All right, let's dive into a core concept in electrical engineering that has, well, surprisingly massive real-world consequences. It's really a story about a tiny, hidden imperfection that creates this huge ripple effect in the technology we use every single day. You know, when you learn this stuff in a classroom, everything is perfect. Every component does exactly what it's supposed to do, every switch is instant. But then you get out into the real world, and things get messy. So today, we're going to explore what happens in that gap between the ideal theory and how things actually work. Okay, so let's start with the perfect plan on paper. We're looking at a pretty basic circuit called a half-wave rectifier. Its whole job is to take the alternating current, the AC from your wall that swings back and forth, and turn it into direct current, or DC. That's the steady, one-way street of power that almost all of our electronics actually need to run. Now, in this ideal textbook world, the whole process is just flawless. When the AC voltage swings positive, bam! Diode 1 instantly switches on and lets the current flow. The moment the voltage swings negative, click, Diode 1 slams shut, and Diode 2 seamlessly takes over. It's a clean, perfect, instantaneous handoff. Every single time. But you knew there was a but coming, right? This is where reality just comes in and crashes the party. See, real-world circuits have a small but totally unavoidable imperfection. It's not on the blueprint, it's a glitch that we're pretty much just stuck with. This glitch has a name, commutating inductance. And no, it's not a component you can just find and remove. It's what engineers call a parasitic property. It's just baked into the physics of the wires and parts themselves. And all you need to remember about it is this. It absolutely hates when current tries to change in an instant. And we're not talking about some rare, exotic thing here. This inductance is everywhere. I mean, literally everywhere. It's in the wiring in your house, it's inside the power adapter for your laptop, and it's a huge deal in things with big coils of wire, like the alternator in your car. So what happens when this little dose of reality gets into our perfect circuit? Well, since inductance fights against instant changes, our perfect lightning-fast switch, yeah, that's not going to happen anymore. The circuit has to play by a whole new set of rules now. So here's what actually goes down. The voltage signal comes in, telling Diode 1 it's time to turn on. But the inductance basically slams on the brakes and says, not so fast. It stops the current from instantly jumping from Diode 2 to Diode 1. And this creates this really bizarre, messy moment where, get this, both diodes are actually on at the same time. The current has to slowly ramp down in one direction while it ramps up in the other. So what's the big deal? Well, the effect this has on our output voltage is fascinating. Professor David Perrault from MIT has a great way of putting it. He says this delay takes a bite out of my half-sine voltage. It literally eats away a piece of the power the circuit is trying to make. Because during that brief moment when both diodes are on, the output voltage just nosedives to zero. And this voltage bite is the root cause of a really critical concept called load regulation. What it means is that our power supply, the one we hoped would be perfectly stable, isn't stable at all. The voltage it delivers actually changes depending on how hard it's working. So here's the crucial point. The more current you try to draw from this circuit, that's what we call the load, the bigger that voltage bite gets. And the bigger the bite, the more your output voltage droops or goes down. So if you're really pushing it at full load, the voltage you actually get might be way lower than what you were expecting. So that's what load regulation is, in a nutshell. It just measures how much the output voltage changes as the load changes. We were shooting for a perfect power source, zero regulation, a totally flat line. But because of that one tiny, unavoidable bit of inductance, what we actually built is a droopy source. Now, I know this might sound like a small academic issue. Droopy voltage, who cares? Well, this droopy characteristic can lead to some massive and very expensive problems in the real world. And a perfect place to see this in action is inside every single car on the road. Think about it. A car's alternator is just packed with coils, which means it has a ton of that internal inductance. So to fight against that huge voltage droop and still charge your 14-volt battery, that alternator might have to generate a whopping 80 volts internally. Now imagine the battery cable gets disconnected for a split second. That's a load dump. Suddenly the heavy load is gone, the droop vanishes, and that massive 80 volts has nowhere to go. And this is the punchline. This is the real-world cost. For a brief moment, the car's entire electrical system, which is supposed to run on maybe 14 volts, gets hit with an 80-volt spike. This means every single computer,
Every sensor, every little electronic module in your car has to be massively over-engineered just to survive this. And it's all because of that one little glitch we started with. So you see how a tiny fundamental imperfection can have these huge ripple effects? It forces engineers to design things not for the perfect textbook world, but for the messy, complicated real one. It's just this powerful reminder that sometimes the most important details are the ones that aren't even on the blueprint. It kind of makes you wonder, right? Where else do our perfect plans run headfirst into a messy reality?